pick these up. If there's not enough handouts, you can go to my secretary, Jerry Hill, in room 4134, right across the hall beneath us, and she can give you those handouts. The difference, you ready? Are we on? 337 has its origins back in the mid-80s when I started teaching a course on welding and joining. In the late 80s, early 90s, I modified the course because the Leaders for Manufacturing program, and turned it into not just a welding and joining course, but kind of add a little more manufacturing stuff. I specifically kept out certain things like welding, metallurgy, fracture, and non-destructive testing, because Professor Masabuchi on ocean engineering taught a course at that time in those topic areas. When he retired about 1996 or so, Professor Chrysostomidis, and at that time it was Captain Brown, head of the Navy program, came and asked me if I would add some of those things I had left out into my course, because they didn't have someone over in ocean engineering to teach what Professor Masabuchi had been teaching, and since he wasn't doing it anymore, it wasn't redundant. So I added 12 lectures and called that 3371, and it has a 13 number. What's 13391J or something? So it has a J number with 3371. The LFMs, the reason this course is at 7:30 in the morning is because I had these Navy students, I had these LFM students, I had course 3 students, I had course 2 students, I've had management students take this course. So there's a number of different students from different departments, and the only time that was common to everyone's schedule was 4 o'clock Friday afternoon, one year when I checked everyone's schedule. So I decided to start teaching before everyone else teaches. The advantage to that is I didn't have to worry about all the other schedules. And so the course used to be from 8 to 9. Then Sloan moved everything back to 8:30 for starting of their courses, and I moved back to 7:30. And when I did that, I realized that's kind of early. However, if it's on video and you want, you could take this course by video this term. I've had students, even when I was lecturing live, essentially watch the video and take it, not live in the classroom, but by video, just like students in the spring term, because they didn't want to get up early. However, I did tell the students that if you're willing to show up at 7:30, I will start promptly at 7:30. I will stop fairly promptly at 8:20, so that if you are an LFM student and you got to get over to a Sloan course at 8:30, you'll have time to get over there. The other thing I said is I will supply breakfast, continental breakfast, for you at 7 o'clock. So if you got to get here early, you don't have to worry about breakfast, okay? And in fact, the best comment I ever got on the course was the student who said, I just want to know what course Professor Eager teaches at lunchtime, okay? So you get a free breakfast. What else do I want to go through in this? Oh, okay, what happened was I used to teach 337 between 7:30 and 8:20, and then I would teach a half-hour version or 25-minute version between 8:30 and 5 minutes to 9 for the course 13 students or anybody else who wanted. That 3371 version really has to do with heavy fabrication. It's kind of directed towards shipbuilding, okay? Ocean engineering, the U.S. Navy. But it talks about fracture mechanics, failure analysis, non-destructive testing, welding, metallurgy, and material selection. So some of it applies to more broadly than just materials fabrication. What happened this summer was 15 of the 13A students decided that they wanted to take the course during the summer by video. When I learned about that, I thought, well, that's sort of silly to have them, the 15 students, taking the course that I designed for them by video. So why didn't I just lecture those 12 lectures live during the summer, which I did. So what we're going to do this year is 337 will be taught in the morning at 7:30. And the days that I have to travel, which are not this week, but are several days next week, you will watch, if you want to sign up for 337-1, you can watch the 12 lectures in 3371 and take the 9-unit course from 7:30 to 8:30. So in fact, I will come up with a schedule in the next couple of days of when I think I'm going to be out of town in the next 2 months. We lecture this class every day of the week that I'm in town live. And the days that I'm not in town, since I have these 12 lectures that I did this summer, you can watch the 3371 video. So there's no reason, if you have an 8:30 class over at Sloan, there's no reason why you can't take 3371 this year. It used to be the Sloan students couldn't take 3371 because I lectured it between 8:30 and 9. But now, if you want, you can come every day, 5 days a week, and we should finish this class, 3371 and 337, together, kind of merged, by Halloween. Okay, that's about 40 lectures. We actually should finish a day or two before Halloween, but sometimes we do things like lab tours and things like that. And there's a couple of other video days of some movies on welding that I think are fairly worthwhile. So. Does anybody have any questions about that? Now, the one complication is 337 was grades and 3371 was not grades. It was pass-fail. So if you want grades and you want to take 3371, you're probably going to have to sign up for special problems for 9 units. Okay? There's a special problems course in material science. If you don't care, if you're happy with pass-fail, you can sign up for 3371, but it's officially graded pass-fail. It's a long story, I don't want to go into it, but next year I'll probably just make both of them grades. So far as requirements in the course, you have your choice. You can either do a homework set, which consists of 10 problems, or you can do a term paper. If you want to do a term paper, you need to come see me for 10-15 minutes, talk about what you want to do your term paper. I'll give you some references, and you can go from there. The homework problems are actually in the handout set about 4th or 5th end. There's something that says Chapter 16, Processes of Joining Materials with my name on it. What happened was about 10 years ago or so, I was asked to write a chapter in a textbook for mechanical engineering for Professor Sue on welding and joining. And the problem, well, it's a long again, that's a long story, but we don't need to go into. What happened is I took my lecture notes home one day, and I spent the whole day at home outlining this course back then. So if you don't want to read anything else in this course, you can just read Chapter 16, which is about 30 pages long. And there's 10 problems at the end. Those 10 problems can be your entire course assignment for the term. You're welcome to do that as a team. The record is 19 students turning in 1 homework set. Okay. But if you do it as a group of more than 1, I don't care if you have 3 people and 2 people do 3 problems and 1 person does 4 problems. I do require that you sit down with each other and go over each problem so each person understands what the problem asked and, you know, how it was done, how the person went through it. I don't know how the 19 people divided it up. I suspect that 3 or 4 people got together, did the problems, and everybody else got together at some time and discussed it. But I don't care. The only reason I require either one of these is because MIT requires me to grade each student individually. Now, I can do that any way I want. And I can have teamwork problems. I can have term papers. My philosophy in this course, because until the 13A students had to take this in 1996, this course was not required for anybody. And the only reason people took it was because they wanted to. And I thought that was great. I used to teach undergraduates, thermodynamics, sophomores, and I would give them real quizzes, and I would try to separate A, B, C, D, you know, and E and F among the students. But in a graduate course that's not required for anything else in your life, hopefully you're here because you want to take the course and not because you got to get some grade in order to pass some general exam or something like that. Okay, so this is a course where hopefully you just take it for fun. Hopefully you're willing to come to class. It gets a lot harder after Halloween, because, or actually the Sunday before Halloween, because we go off daylight savings time and you start coming in the dark. Okay, that's one of the reasons. Well, I switched to this every day of the week when I became department head 7 or 8 years ago because of my travel schedule as department head. I've kept it because what I've learned is once you hit Halloween and all the other courses start gearing up, and it starts getting dark when you come in at 7:30 in the morning, the students have a harder time coming in. So we kind of compress this course every day of the week for 2 months, 7:30 in the morning, free breakfast, come, enjoy the lectures, sleep through the lectures, whatever you want to do the homework set or a term paper, I don't care. So I have to have something with your name on it in order to give you a grade. I wouldn't worry a whole lot about the grade. I've only given 1 grade in this, or 2 grades in this course in my life. Or actually 3 grades. I either gave passes, incompletes, because someone hadn't turned something in, or a letter grade. And I won't tell you what the letter grade is, okay? But I've never given anything but 1 letter grade. And all the rest of the faculty know, and they think that's scandalous that I would just give 1 letter grade. But what do I care? You know, you're graduate students. It doesn't really matter. The grade you get in this course will not have any influence on your career for the rest of your life, I guarantee you, okay? So we're not interested in grades, but I still have to grade you. It's MIT rules, okay? Any questions? Since everything is open, I don't know how you could cheat in this course, okay? Actually, I do know how people cheat. I know they use the same problems for years I've been giving out. Someday I'll write some new ones. And what they do is they go back and take someone else's solutions from previous years, which is fine, I don't care, as long as you've gone over and thought about it. I got through MIT as an undergraduate because I had the Bibles of my house tutor when I was a freshman, and he was the brightest student to go through the department in 15 years. And I used to go through his home, and the professors used to give the same problems. And I would do the same type of thing. I would take his solutions, and I would study them and make sure I understood them. But I didn't have to go through all the pain and agony of figuring everything out. I'll warn you a little bit about the homework problems, aside from the fact that they've been handed out for years. About half of them, or maybe a little more, don't have a fixed answer. You know how you learned in high school that if the question has 4 pieces of information, you have to use all 4 pieces of information, and they never give you an extra piece of information. And they always give you enough information. They never give you too little, right? And so students are very clever. They figure out, well, I have to figure out how to use all these pieces of information. Well, the world is not like that. When your boss comes to you and says, I want you to solve this problem, he doesn't say, and these are the 4 pieces of information you have to have. If he gave you that, he could do it himself. He or she could do it himself. So some of the problems are open-ended. They don't have a solution. In fact, one of the problems, over the years, I keep on getting solutions from students, and I don't know what the answer is, okay? I'm so confused with this problem now that I'm sort of sorry I asked it, except it's kind of interesting to see all the creative types of solutions I get. Some of the others, I get kind of the same answer all the time. Problem number 1 is that way. I usually get the same answer. There's one problem in there that I made a mistake on. I asked you for a maximum velocity and a minimum velocity, and the minimum velocity turns out calculates to be faster than the maximum velocity. So there is no solution, okay? And sometimes that's the way it occurs in the world. I could have gone back to correct the problem. I actually made the mistake when I wrote the problem, but I decided, why correct it? Because sometimes that's the way it works. Okay, you have 2 constraints and they are exclusive, and there is no known solution. So that's where you can figure those things out. So that's my name and number. There is this web address if you want to. Last year I had a student sit and take fairly detailed notes of the lectures, and someone's doing that this year. Who's doing that this year? You're doing it, okay. And so that will be posted on the web. We'll have to talk about that. There's also, Chris Musso and Doug Cannon will be videotaping the course. I need to hire a couple of people to take care of breakfast. Would any people like to earn an extra $500 or $1,000 a term for coming in, going by Au Bon Pain your way, and having the other stuff? The juice and other stuff we can get at Costco and things like that. But getting here about 7 o'clock and starting the coffee. If anybody wants to volunteer now, If you're interested, then we can talk after class about that. Otherwise, you're going to end up with things like Dunkin' Donuts or Costco croissants or something. But what we generally have had is au bon pain, which is a little bit better. Okay. Any questions on that? And if there's certain things you want for breakfast, let me know. If you were down there if the breakfast is in 4133, if you were down there this morning, you notice that we just had Dunkin' Donuts because I picked them up at 5 o'clock this morning. But, and then there's a bunch of, oatmeal bars and Rice Krispie treats and things like that. I learned one year that people actually were taking a few extras. They were actually going down there after class and taking things for their mid-morning snack, which, again, I don't really care. If I was a graduate student once. Well, actually, when I was an assistant professor once, and I used to hold group meetings with my students, and we'd have lunch meetings, and I would go to the grocery store and pick up cold cuts. And as an assistant professor, I was having a hard time, supporting my family on an assistant professor salary, and I didn't have much consulting back then. And I used to keep the leftover cold cuts and take them home to feed my family. Now, when we have group meetings, I let the students keep the food because I actually can feed my family now. But I remember what it was like to be an assistant professor and a graduate student. So if you need a mid-morning snack and you want to take some, I don't care. It's not a big deal. I can probably afford it out of my discretionary funds. Okay, I think that's all the introduction. Anybody have any questions? This is actually a little bit bigger group. Some new people came in. I'd asked before, how many people were, some of the people in the back, LFMs, a couple. What departments are other people? How many people are course 3 out there in the back? Okay, so I've got, wow, this is the largest group of course 3 students I've had in a long time. That's good, because Professor Suresh was asking me to teach another course this term, and my response to him a couple of weeks ago was, I've got plenty of research, I'm chair of the admissions committee, I teach the second largest graduate course in the department, the largest graduate course in the department after the core courses, and I don't think I need another teaching assignment, for which I didn't hear anything else from him. But anyway, but I have gotten flack in some past years because I only had 2 or 3 course 3 students in the course. But they're usually about 20 or 25 students. So if you look at the handouts, and there's a couple left up here, but you can get these from Jerry Hill, my secretary downstairs. She's got plenty, so you need to go by and pick those up from her. Everybody needs to go by and pick up the 3371 handouts, so far as that goes. The first thing here are selected comments from evaluations in the past, which are kind of the good and bad of things, and I think it's probably worth reading that one page just to get a feel for some things about what the course is like. But again, the main purpose of the course is to try to talk about things and learn some things. And to me, it's not really a course in welding and joining. In fact, did someone just take the top off this? I don't know. Anyway, that looks like only a partial set. To me, it's not really a course in welding and joining. This course is really a course in how to think about engineering problems. It's also kind of a course in philosophy, and you'll hear about that in terms of stories. I like to tell stories. And in fact, I really like digressions. And so if you don't come up with some questions so that I can digress and ad lib, then I'm going to have to digress on my own so far as that goes. So it's usually sort of a challenge to see if a student can ask a question, can I come up with a story out of the blue to reinforce that question. I guess the next thing is, if it's not really a course on welding and joining, why study? Or why do I bother to teach welding and joining? Well, for me, the simple answer is it was a way for me to get tenure. At a university, you have to have, in order to get tenure at a university, you have to have impact in some field. And I remember what John Kahn, who was a faculty member here when I was a student, but a very well-known material scientist now at NIST, once said, get into a backward field, it's not hard to be a star. Okay, now if you get in an advanced field where all the bright people are working, you're going to have a hard time rising above the crowd. But if you get in a backward field where there are a lot of people who haven't really done a very thorough job, or you get into a field where there's a lot of unsolved problems, then you can be the first person to solve a problem. And in fact, I remember a student came to me back in the mid-'80s. He was funded by Lawrence Livermore, and he wanted to study welding of stainless steel. And I said, John, why do you want to study welding of stainless steel? There's 10, 12 people in the last 20 years who have studied that topic. What are you going to do that's new? I mean, that's a plowed field. You're not going to find any gemstones after 10 or 12 people have already plowed the field. And no, he really wanted to, and he was funded by Lawrence Livermore, so he did, and he actually did a very good thesis, and he actually found some gemstones in that field. But my philosophy is try to think of a field, go find a field where no one has ever plowed it before. And then anything you do is new and different. Give you an example, particularly we have a lot of material students here. Polymer science is that way today, okay? Or nanotechnology. You know, and we're going to go through the strength tomorrow probably, the strength of bonds, and which is kind of fundamental to material science. You know, what's the strength when you bring two atoms together and what force does it take to pull them apart? Well, Richard Smalley won the Nobel Prize for discovering carbon buckyballs, fullerenes, and carbon nanotubes. And someone in his laboratory calculated the strength of a carbon nanotube and calculated that these little nanotubes would have a strength of 2 to 3 million psi. That's pretty impressive, isn't it? Because most materials are around 100,000, 200,000, so this is 10 times the strength. Except that in the 1950s, people calculated the strength of iron whiskers as 2 to 3 million psi, and they actually made them and measured them. And they were around 1.5 to 2 million psi. So there's nothing new, except that the physicists down at Rice University in Houston did the calculation and then didn't bother to check the literature to find out that other people had already done this 40 years before. And so they have now convinced most of the people in Washington that if you take these little carbon nanotubes and you put them in some structural material and make a composite with these things, it'll have fantastic strength. So what do you think the likelihood of that happening is? If we had the iron whiskers since 1950, but we also had something else, very fine little fibers that we used to put in composite materials to strengthen these composites. It's called asbestos, okay? We were putting asbestos fibers in to strengthen concrete and other materials for decades. Now, we quit using asbestos for health reasons, but we were putting little strong, not nanotubes, but something just as strong as a nanotube, in these composites, and they were somewhat stronger. I mean, if you made more, asbestos mortar had more strength than mortar without asbestos, by about 10 or 20%, big deal. So these people are predicting fantastic properties, but anyone who looks at the literature and understands what's going on realizes that we are plowing millions of dollars into a field that is going to, in 5 or 10 years, come up with the conclusion that the carbon nanotubes really don't quite reach the potential. Now, that's a fairly common thing. There's a quote by Bob Sprague, who was head of materials at GE Aircraft Engines. And I actually have an overhead, but I didn't bring it. He says, whenever you first hear about the properties of a new material, write it down, because those are the best properties that material will ever possess. Okay? And Jim Williams, who's now dean at Ohio State and used to be dean of engineering at Carnegie Mellon, but in between replaced Bob Sprague as head of materials at GE Aircraft Engines, has a corollary. He says, whenever you hear about the cost of a new material, write it down, because that's the lowest cost that material will ever possess. Okay? So that's actually part of the material selection lecture in 3371, so far as that goes. But why bother to study welding and joining? Well, it got me tenure, but that's not really the reason. It got me tenure because there is a community out there of people in welding and joining, and they could write letters and say, oh, he discovered this and he discovered that. Well, that's because no one had ever looked for it. basically, I like to tell the story that I learned this philosophy when I was in second grade during an Easter egg hunt. And we were all searching around this backyard looking for Easter eggs, and one person says, "Oh, I saw one!" And then everyone ran over there. Only I was kind of late, and I was looking at the back end of most people, and I thought I couldn't even get there to see where they were looking. There were so many people around. And so I decided this is sort of silly, and I went over on the opposite side of the field to look for Easter eggs because there was no one there. And I found that I could find Easter eggs where other people were not looking. But when I was looking where other people were looking, the odds of finding it were slim. Okay? And that same philosophy is basically what I've used in research over the years. Don't look where everyone else is looking. Try to think of an important problem where no one else is looking, and then solve that. Anyway, one of the other advantages of welding and joining is I never wanted to get in too deeply into something. You know, the typical way to get tenure at a university is to study some topic in excruciating detail until you know more about it than anyone else in the world. In fact, one time, my daughter, who is now in her 20s, and just had a son 2.5 weeks ago. But Linda came home when she was 10 or 11 years old, and she said, "Daddy, Mr. So-and-so down the street says you're the world's expert in your field." I said, "Linda, if you define your field narrowly enough, there is no one else." Okay? And so typically at universities, people will study more and more about less and less until they know everything about nothing, if you've ever heard that quote. Well, I didn't really like that approach. And welding and joining allows me to work on physics, chemistry, mechanical engineering, civil engineering, materials engineering, chemical engineering. I can work on all kinds of things because there's some little piece of it that applies to welding and joining. And hopefully by the end of the course, you'll kind of see that. Also, hopefully in this course, not only will you find that there's some integrative aspect to it, this is where we literally put all the things together in a joining course, things that you've learned, but you'll also hopefully learn how to simplify things. Another thing I learned over the years when I was a student was that some professors like to make things more and more complex because then it seems like they have this great knowledge which they're imparting to you. And the more complex and confusing they can make it, the more it builds up their ego. Whereas really the best teachers, I mean, Professor Cohen in this department was a fantastic teacher. I remember taking courses from him as a junior, and he would explain ternary phase diagrams, you know, these three-dimensional objects. But as he was explaining it, everything was crystal clear. You knew exactly what it was until you walked out of the room, and then you couldn't explain it to yourself. Okay, but he made it clear. And that's good teaching. You take something that's complex and make it simple is actually good teaching. To take something that's simple and make it complex is not teaching at all. It's just ego building. However, a lot of ego builders on the faculty around here. Anyway, so it's integrative. It integrates all kinds of things that you learn in other things. It actually turns out to be important for a number of reasons. It's important because it's improved what we make in a number of ways. It's increased the size of what we can produce. If I'm a naval engineer, and I look at the ships, the battleships they built in 1900 for, Commodore Dewey and Manila Bay and stuff. Anybody have an idea how big those ships were? They actually weren't as big as the destroyers we have today, okay? But within just 20 or 40 years, they were building these 1,000-foot-long battleships with 17-inch thick armor, okay? Could you imagine riveting 17-inch thick armor? You know, put two sheets of 17-inch thick material and put a 36-inch rivet through it? That sounds sort of silly, doesn't it? Except that if you go over here to see the USS Constitution, that's basically how they put that. They put a bunch of wood ships together, and they might be 16 inches of wood, and then they had these 36-inch long brass rods that they are copper or brass. Can't remember. They might have been brass. that they would put in there. And it turns out that was a key technology during the time of the Revolutionary War. And the person who brought that technology to the United States and stole it from the craftsmen in England was a guy named Paul Revere. Because think about it. You got two big pieces of wood that you're going to stick together, and you're going to drill a hole. You can drill a straight hole between those two, 10-inch thick beams or whatever. And then you have to knock this rod in there to kind of rivet it together, or hold it to this pin, this brass pin to knock it together. Well, if that rod isn't perfectly straight or uniform in diameter or circular, you start hammering it in there, and all they had was hammers back then. I mean, there might have been big sledges, but that's all they had. And if it's not perfectly, if that hole's not straight, and if the rod is not straight and circular and of the right diameter, it's going to get stuck in there, right? And you won't get it all the way through. And what good is a pin that only goes halfway through? So it turns out there was a technology, and we don't know what the technology was. That's been lost for the ages. Although Professor Leckman once got it for the people over here at the Constitution were repairing the ship, and they got one of these pins, and they gave it to her and allowed her to cut it up. And she asked me to come over one morning to look at it with her and try to figure out how Paul Revere might have made this thing. Because he went over to England and he learned the technology. So this is military espionage a la 1790, right? And he brought it back, and we were able to build ships of the line. That also occurred in World War II, when they were welding the 17-inch thick armor for the battleships. Most of you were probably too young, but 15 or 20 years ago, when there was an explosion down in Puerto Rico or somewhere in one of the battleships. In the magazine, one of the this was the Iowa or something, was one of the last battleships built in World War II. Anyway, they had an explosion that killed a few people, and the Navy never completely repaired that because no one knew how to weld the armor together in 1980 that they had been welding in 1985. They had lost the technology. All the people had died. No one knew how to weld a 10-inch thick plate together without stress relieving it to prevent cracking. So the Navy never completely repaired it, but that's okay. But welding has increased the size of things. Bigger, longer pipelines, bigger bridges, taller buildings, because we can weld and we can save weight. Welding allows you to get rid of flanges. If you're going to bolt things together, you have to have these big, heavy flanges, and that's a problem. Welding also has reduced the cost of what we produce. If you go back 400 years ago, people, and you go up here to Saugus Iron Works, and you look at how a nail was made. A nail was made by starting with a big piece of pig iron and hammering it into a rod, and taking those rods and pulling them into wire, and then hand forging each nail. As a result, nails were so valuable that after you built a house and you put nails in to build the house, when the wood rotted, you would burn the house down and sift through the ashes to recover the nails, because the nails you wanted to reuse. There was so much work that went into them. Well, of course, that's not welding necessarily, but just in general, manufacturing has seen thousand-fold productivity increases in the last 400 years in many industries. Welding has contributed significantly to that. If you go back and you look at big pipelines they built in Maine, I had to work on one of these things. 100 years ago, they were building a hydroelectric plant in Maine, and they didn't have a way to weld pipes together to carry the water for the hydroelectric plant. So they took sheets, and people hand forged the sheets into cylinders and then riveted them along the length, and then riveted them together along the circumference to join these things together to make a pipeline. Tremendous amount of work, hand work to do that. Starting in the 1930s, they built the first gas pipeline that was welded. 30-inch, they called it the Big Inch. It was a 30-inch pipeline from Texas to New Jersey, and it was one of the first critical welded structures. Critical because if you lose a gas pipeline, you have a very big fire. In fact, we had one in Edison, New Jersey about 15 years ago. I think it was a 42-inch pipe, gas pipe, 900 psi gas, let go, and they had a 600-foot flame right across from apartment buildings. In fact, it melted the asphalt on the apartment buildings. It was the middle of the night, and no one got hurt, although a woman 3 miles away had a heart attack, and they blamed that on the pipeline explosion and died that night, but who knows if that had any relevance. In any case, there can be big problems that occur from some of these things, and we'll get into that in a second. So it's also improved the reliability In fact, I often say that the quality of a manufactured product is directly related to the quality of the joints. Back in the mid-'80s, I purchased two new cars within 1 year. I had 6 warranty repairs. These were American cars, and that was average for an American car in the mid-'80s. A new car would have 3 warranty repairs. Nowadays, it's about 1 for a new car. A new American car is about half for a Japanese car. But in any case, I had about 6 failures that I'd take those cars back because this light didn't work or that didn't work or whatever. Every single one of those failures occurred at a joint. I remember when the Space Shuttle Challenger went down, I was in the office where my graduate students had their desk when we heard about it. It was about a half an hour after it happened, and the space shuttle failed. And I said, I bet it failed at a weld. Well, I was wrong. It didn't fail at a weld, but it did fail at a joint. It was an O-ring joint. And so things tend to fail at some of the most, at the joints, and we'll get into that in a second. Another reason why welding is important is it's ubiquitous. What does ubiquitous mean? It's everywhere. Ubiquitous means everywhere. Everything you can think of just about contains a joint. In fact, here's your first quiz question. There's no grade on it. Think of the largest standalone object. By standalone means it has a function. It's not just a paperweight. Actually, a paperweight has a function. But that you can use it that does not contain a joint. The largest standalone object. I used to get nails, paper clips, pins, but you can think of things that are larger. I once said this on a trip with some other MIT faculty. Professor McClintock worried about this for a day. And finally he came back. Someone actually came up with one, a cast iron frying pan. Okay? But notice you have to say a cast iron frying pan, because if you said an aluminum frying pan, you don't have aluminum handles on the frying pans. You have a plastic handle, and so that's actually one principle. If it's not a monolithic material, it's going to have a joint in it somewhere, because you have to join the two dissimilar materials. So a regular frying pan, which is made of plastic handle and an aluminum pan, is going to have a joint in it. It may be riveted, but it's still a joint. But if you say a cast iron frying pan, well, you can have a cast iron frying pan, and gee, they can be 16 inches in diameter if you're strong enough to lift it, right? Professor McClintock came up with an anvil. Okay? Now, anvils can be pretty big. But you can see if you can come up with something better. I will tell you that the largest metal object made weighs 700 tons, but it's not a standalone product. It's a generator rotor forging. And they have to have several steel furnaces going at once. And they pour everything from one furnace, and then another furnace, another furnace. It takes them about a day to pour the 700-ton casting. And then they forge it. They end up with about, after they do machining and everything else, they end up with a rotor for a generator for an electrical generation plant. It'll generate about 1 billion watts of electricity per hour. 1,000 megawatt electric is what they call it. And they can only produce a few of these. a year. In fact, the United States has 2 facilities where they can produce these. The French have one, and I think the Japanese have one. I'm sure the Soviets have one. The 2 facilities in the United States, one was at U.S. Steel and one was at Bethlehem Steel. They were built in World War I, or before World War I, to make battleship gun barrels. To reproduce those facilities would cost $3 or $4 billion today, which is why no one does it, because, in fact, no one could afford to build those things today. There's just not enough money in it. So see what you can come up with, and you can tell me tomorrow about the largest standalone object, if you can come up with something larger than an anvil. And some students have over the years. Another thing is there are many failures that are attributable to welding. Professor Pellew, who's retired from this department, used to teach fracture. When I was a young assistant professor, one of the students came up to me, did you know that Professor Pellew in his fracture course says something won't fail unless it's been welded? And at first I thought, wow, I'm in welding, what is he saying? Something negative. And I thought, wait a second, it's okay. As long as they keep failing, I got a job. Okay. In 1992, I had to give the Houtremont lecture in front of the International Institute of Welding, and so I put up this overhead. It says, something won't fail unless it's been welded. Reggie Pellew, Professor Regis Pellew, MIT. And it was dead silence. 500 of the world's leading welding engineers, dead silence. And then finally, a little ripple of laughter started going through the room. They didn't necessarily appreciate it. Now, Professor Russell, who's recently retired, used to have a corollary. He says, or cast. So castings fail too. But why do they fail? Welds fail. The failures usually occur at a joint. I've already made that point. But the joints are located at the most highly stressed locations. Think about it. If I'm building a simple box, where are the joints going to be? They're going to be on the edges and the corners, right? Well, where's the maximum stress? If you're bending something, it's going to be at the corners and the edges. So the welds are often located at the most highly stressed locations. So it's not necessarily the weld is inferior, it gets stressed more than the rest of the structure, and so it tends to fail at the welds. However, sometimes the joint is weaker. In some materials, like high-strength aluminum, heat-treated aluminum alloys, we do not have a way to make a weld in a high-strength aluminum alloy that has full joint strength. And we'll get, as we get into the course, we'll talk about some of that. And therefore, you often have joint failures at the joints. However, because of that, the designers of high-strength aluminum structures tend to locate the joints at other locations than the corners, and therefore avoid failures at the welds. So it is possible to do some of that. There are many failures. Welding is often applied as an art. I've noted over the years that every time someone develops a new heat source, one of the first things they do is try to use it to weld. When Sir Humphrey Davy discovered the arc, somewhere around 1807, he named the arc. He had 2 electrodes, and he was playing around with electricity, right? And he pulled them apart, and he got a plasma discharge between them. They were horizontal electrodes, and it formed an arch of plasma. So he called it an arc because of the arch of the hot gases rising due to gravity, buoyancy. So then in the 1870s, as electricity became more plentiful, readily available, as Edison and Westinghouse came along and started building generators, people started welding, using arc welding. One of the first applications of lasers back in the 1950s, you remember the lasers were only developed like 1958, General Electric was using lasers to repair vacuum tubes. Because vacuum tubes might cost $100, but if you had a failure of a joint, you'd have to break the vacuum and go in there and re-weld it. And they found that you could shoot the laser light through the glass in the vacuum and re-weld the joint in situ without breaking the vacuum. And so one of the first applications of lasers, commercial applications, happened to be in repairing vacuum tubes. One of the first applications of electron beams was to try to weld with them. I learned a few years, about 10 or 12 years ago, when the Navy and the Defense Department developed particle beam weapons. These were electron beams that were supposed to be able to shoot 30 miles through the air and shoot down an incoming missile. So you wouldn't have some missile destroy the ship. The government spent $250 million developing these particle accelerators. And one of the first things that people did after they got these beams up and running is they tried to weld some things together with these particle beams. Turns out it wasn't a very good weld for various things, and we'll talk about why. Welding processes are complex. I've learned over the years that one of the reasons that there are relatively few people who work in the field of welding at academic institutions is because the problems are too hard. I got a lot of research money in 1980 from the Office of Naval Research and went right down here to the spectroscopy lab, and I said, gee, I want to study plasmas. And they said, oh, well, because that's where all the plasma, if you look at the roof of the building right out here, the MIT spectroscopy lab, that's where the MIT wavelength tables the world uses were all developed right there. And I went over to talk to some of the physicists, and I said, I've got some research money from the Navy. They want me to do research in welding. I'd like to do some spectroscopy on arcs. Would you like to work with me if I give you some research money? They said, oh no, we're not interested in that. And so, those problems have all been solved. Really? Okay. What I later learned, as I learned more about plasmas on my own, is physicists don't like to work on welding arc plasmas because a welding arc plasma is a partially ionized plasma. They would much rather work on weakly ionized plasmas, like where less than 1% of the atoms or molecules are ionized, because then you can treat the problem as a single electron or charged particle surrounded by a bunch of neutral particles. Or they like to work on a fully ionized plasma, where each charged particle is surrounded by a bunch of other charged particles. They don't like to work on something that's where 20% of the particles are charged and 80% are not, because that makes the mathematics really messy, right? As Theodore von Karman, anybody know who he was? He was basically the guy who explained what the Wright brothers did. He was a professor at Caltech and one of the great engineers and scientists of the first half of the century. Von Karman said, a scientist explains that which exists, an engineer creates that which never was. And I've always liked that quote because the scientists think it's a great quote, and the engineers think it's a great quote, and they both disregard each other. Any case, but von Karman explained it. Welding processes tend to be complex, and therefore it takes a little bit of creativity to try to figure out how to simplify it. Another problem, I'll finish up here. Few engineers are trained in welding. And you'll find all, so far as notes, you can go copy the notes from last year off the web. There's actually one other thing that I'll go over, but just to finish up here with few engineers are trained in welding. It turns out that this country produces about 20 to 30 welding engineers a year, whereas in the Soviet Union they produce a couple of thousand, or the former Soviet Union. In Europe they produce hundreds, and the Japanese produce hundreds. Welding is considered an interdisciplinary field in the United States. As a result, no one really gets trained in it, but some boss will say, we've got some welding problems, you're now a welding engineer. That's exactly what happened to me. I went to work for a steel company when I graduated from MIT, and they said, you're a welding engineer. I didn't know anything about welding. So you learned it on the job. And that's good in the sense that many people don't learn it very well, and there's lots of problems, and that keeps me in business. But it's not necessarily good for the economy that people don't understand the differences between different types of welding processes. So those are some of the reasons for studying it. Tomorrow we will get into the final reason or two. about the limitations of welding on materials, and then we'll start talking about cold welding. And I didn't show you some of the, I'll show you some of these products that are made by welding as well. Thanks.